There we go. So it is my great pleasure to introduce the last speaker of our colloquium for this fall semester, Daniel Gonçalves from Universidade Federale Santa Catarina. He's going to be speaking to us about Leavitt path algebras and their generalizations, where dynamics, algebra, analysis, and combinatorics meet.
Okay, so thank you very much, Sergio, for the invitation. Thank you, Adam, for also. It's a pleasure to speak. And about have the title, right? The aim is very high, right? To talk about all these topics in one talk is pretty much impossible. So just give a small picture, a little the tip of the iceberg of everything that can be done, and I'll try to give an idea of how these graphs come into play when we study dynamics, algebra, analysis, or combinatorics. So that if you like any of these topics, it's something that you can maybe follow up later. Maybe there'll be a little bit more of dynamics, but we'll see. We'll see as it goes. It'll be a little bit of everything. So if this will just work. Okay, so the first thing I want to talk about is why do we want to use graphs or study graphs, right? So for example, if you just have a simple graph here, right? Two loops, and let's say I have two edges here, E and F, and my space will be just then I'm going to be looking at as a set of the space of infinite sequences of edges, so I can, which are really infinite paths. So in this graph, a path, right, is I will have like, for example, E, F, 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 E. I can do anything here, right? So, well, maybe this is not a very good example, but if I start a little more slowly, if I have an edge, it has a big initial vertex and a terminal vertex. And I can follow this edge by another one if the terminus of this one is the initial vertex of the other one. And so once I have this, I can look at infinite paths. Okay. So then we have a set of all the infinite walks or infinite paths you can do in a graph. Okay. So we'll be looking at these objects, and we have a topology in this space. But why we want to look at this, right? I said, so let's suppose one of the main ideas, this is right, this is the way to code shifts of finite type, which are very much studied in symbolic dynamics. And the idea that comes behind to study the symbolic dynamics is to code any dynamical system. So let's say you have a dynamical system. Let's suppose for a moment we have a map from the unit interval to itself. The unit square. I suppose that this is 0, 1 here, 0, 1. And so this is R. And we have a map T that goes from R to R. So this map could be anything. I could just take, I don't know, could take a pair X, Y and take it to X plus theta mod 1, comma, I don't know, X plus theta, Y, sorry, Y plus theta prime mod 1. Some irrational rotation in both coordinates. And when you're studying dynamical systems, you really want to understand the orbits. So you want to iterate the map. So you take a point here, let's say X, and then, okay, I have this point X, and want to study the orbit, see what happens, right? You want to see how the system evolves. So you look at T of X, T square of X, T cube of X, and so on. Okay, I don't know, so maybe T of X is here. T square of X could be here. Well, so on, right? This goes on the. So when I want to, but now let's say I want to, where does this coding comes? So let's say I divide my unit square into two squares. Oh, sorry, two rectangles. And let's label the top one 1 and the second one 2. Okay. Then I'm gonna kind of code this orbit by saying, well, point X is in rectangle 2. So I'm gonna take this point X here. It's gonna go to 2. Then look, T of X is at rectangle 1. T square of X is in rectangle 2. Let's say we have T cubed here. Well, it doesn't need to be always like this. This is going to give you a wrong impression. Maybe T cube of X is here too. T cube of X. Then I'll go to 2 and so on. Right. So I'm looking at the orbit here, and I'm coding it with this. I'm saying where each orbit is landing in which subrectangle there. So if I want to apply the map here and apply T, what happens? X will go to T of X. My T of X will go to T square of X, T cube of X, and so on. All right. So if I look at this code that I just described, and I put it and I go down here, well, T of X was in the first rectangle, right? So it goes to 1, T square was in the second, 2, 2. So what I did was, if I look at down below here, was to just erase the first entry. So that's the shift map. Okay. And so what we had now here is a sequence of 1s and 2s, and this map T here, which was just some map in the unit square, is now just became the shift map where you erase the first coordinate. So so that's the idea, right? We're gonna be studying this shift map here instead of studying the map T. And if you look at this, okay, I just had 2, I just divided the rectangle in 2, but I could code this as well as this is my first example, but I had edge 1 and edge 2. Oops, let me here, right? So one vertex only in this graph, and so I'll have like all the infinite paths here are just sequences of 1s and 2s, and so this, of course, is the full shift. And so we could see this as a coding a dynamical system. And of course, these maps could have restrictions, and these restrictions show up many times in these graphs. Okay. And just as a final comment, right? Notice that this set is really just a counter set, right? Sequence of 1s and 2. You're just looking at the counter set.
Sorry, is the sequence 2, 1, 2, 2? Is that you, etc.? Is that would that be uniquely determined by X? Could a different point have the same sequence?
Yeah, it could.
Okay.
It could. Then would have an onto map, right? We'd have a factor here.
Okay.
So there's some conditions. Yeah, you could. So so just if you have any graph now, like one of these ones that we wrote, as I said, we're going to be looking at the sequence of all paths such that okay, so the sequence of edges such it's a path. So you just want to write this. So the range of En. So the terminus, the range is the terminus of the edge is equal to the initial, the beginning, the source of the next edge. Okay. So this is the space we're going to be looking through the talk. And if you want, you can also put a metric here. It's just really, you just put like the discrete topology on the set of edges, and you just take the product topology. But if you want, you can define a metric. So when you have two infinite sequences, you just look at the first. It's the distance between these two sequences, 1/2i, where I is the first time that they differ, right? You kind of go comparing the infinite sequences. There's an entry, the first entry where they are different, that's the I you're looking. Okay, so so we have that Ej is equal to Fj for 1 less equal than j less equal than I, and or this is just less less than I, and then we have EJ different than FJ. Okay. Well, just giving the product topology. Just settles the Cantor set, right? So here's the metric. So you can also think of maybe partitioning this in more rectangles, in more subsets, even infinite ones, right? I could get subsets of area 1 over 2i and partition this over infinite number of subsets, and then we'll have something different, and that's kind of a little bit of the aim of the talk. Say a little bit what happens when we have infinite edges, right? This is when we're really coding by infinite. So, well, I just wrote there, right, the definition of the edge shift. So given a graph, so any graph here that you like, for example, this one, the shift space is just the set of all infinite sequences of edges, right? But they're actually paths, not just any sequence. And they have the pro-discrete topology, right? So I already mentioned this. That's the usual definition for when you have a finite graph, right? When you have an infinite graph, then you have options for the topology, as we'll see in a few minutes. Okay, I didn't. Okay. So I already told you how to associate to a graph a topological space. We have the spaces here. The topology is I already mentioned to you what it is. I'll tell you now how to associate an algebra to it. So let's say we start with a graph E, and we have any unit of ring. But you can think, if you want, of the of a field. It's not too bad to think of a field. It's very usual to just have a complex number, for example. So if you have the graph, we want to define the Leavitt path algebra associated to it. Okay, so what we're looking at is an algebra generated by the set of vertices and the set of edges. And for each edge, E, we create a ghost edge. And we call it E star. And then we have some relations that these vertices and edges have to satisfy. Oh, no, I just erased, sorry. Maybe I'll just put all the relations here so I don't erase my drawing. Sorry about that. But anyways, these vertices, they are mutually orthogonal, and they are idempotents, which are just, if you're in the sister algebra, if you're in the analysis guy, you're looking at a projection. Then I'll write all of them here. So 2 here, so we have an edge, E, and I have the source of E, range of E. So if you're in sister algebras, you really should think of E as a partial isometry. Okay, so and so as source of E is the initial projection of this partial isometry. The range of E is the final projection. So you have this condition, right, that the projection at the source times E is just E, right? And E range times the final projection is again just the image of the projection. The same thing with the stars. So the range of this partial isometry should be orthogonal. That's what condition 3 is saying. So this right, I had a ghost edge here. So what I'm saying on 3 is that the range of the partial isometries are orthogonal, but I'm also saying that the projection E star E is the projection of the range of E, right? So which is a bit crazy. And finally, we have the final condition, which is the Kunz-Krieger condition. So this is usually called CK condition, Kunz-Krieger, which is telling me that if I have a vertex V where there's only a finite number of edges coming out of it, then when I look at this projection of V, this is the projection of V is the sum of all the final projection of the edges departing from V, right? So if I have E1, E2, E3, it's a little bit silly to say, right? So I have the projection of V, is the sum of the projections at the ranges, right at this is the final projections. But this is this thing to fix for the notation that we have for composition of functions, right? That we do f of x and not x evaluated f. So we can change this, but then you change the way your paths go, and then of course there's people that work one way, people work the other way. I have worked both ways, and so sometimes I mix it up. But in algebra, usually this is the notation that's used. In sister algebra is more the other way, but that's okay. So just a few examples. So in Leavitt path algebra, they used to say that there are 3 colors to Leavitt path algebras. There are 3 key examples that if you want to, for example, if you have a hypothesis about these algebras, you should first try in these 3 examples to see if it works there. So one is just this single loop. So I have one vertex and one edge. So if we recall our relations, we had one that said that E star E is equal to the range of E. Right, so I'm looking now at the algebra generated by this edge and vertex. So it's actually 3, right? I'm looking at the edge generated by these guys in E star, because I had this ghost edge. And I know that it satisfies some relations. So in particular, E star E has to be the range of E, which is just V. And the Kunz-Krieger relation also gives me the same thing, right? V has to be the sum of all edges departuring it. I didn't even direction. E star, right? So with this, you can also see that V is an identity. If I didn't call this edge of E, if I had called it of X, right? Let me erase that. What we have here is clearly, right? I had X minus 1x is equal to 1, and X minus 1 is equal to 1. So what we get is that the Leavitt path algebra of this graph is just the Laurent polynomials in one variable, right? So all polynomials in this one variable. If you look at okay, so this is a simple example. Another example is well, I don't want to talk much about this one, but in sister algebra B02. So in Leavitt path algebra is just the Leavitt path algebra of type 1, 2. So this is the Leavitt path algebra. Sorry, this is the Leavitt algebra of type. It's not the path, it's just the algebra. So Leavitt have studied these algebras in relation with the invariant basis number. So you recover his algebras of type 1, 2, if I'm mistaken. Yes, 1, 2. And the third example, which I do not want to elaborate much, but it's simple to check, is if you just have a simple graph like this, and let's say I have V1, V2 up to Vn, then what we get here is that Lk of E is the n by n matrices over the ring or the field. Okay. So this is not all. So you can see that this E here will be a set of this special made the EIJs, right? The matrix, there are 1 at IJ and 0 else. Okay, these are 3 key examples. And the nice thing is that you can get many algebras as Leavitt path algebras, many algebras. Okay, so if you want to go now to the sister algebra world, if you are in analysis, you can get the graph and you can associate with a sister algebra, which is called the graph sister algebra. And the definition is basically the same. It's a universal sister algebra generated by vertices, edges, and then since you're in a sister algebra, you already have the star, and satisfies the conditions associated with that we had here for the Leavitt path algebra. And universal here, if someone doesn't know what it means, is just that if I have my sister algebra E, and I have another algebra here, an algebra A, that satisfies, some generators that satisfy the same relations as the ones that define C star V, then we have a homomorphism from here to there. Okay, so that's what the universal means there. And what is interesting to note here is that the graph C star algebra can be seen as the closure. If you look at Leavitt path algebra over the complex numbers, the graph C star algebra is the closure of the Leavitt path algebra. Okay, of course, under a suitable norm there. So the Leavitt path algebra is dense inside the graph C star algebra. So here we have now analytical object and the algebraic one, and to understand the relation between the two of them is also very interesting. Many properties of one you can relate to the other, but up to today we don't have a clear venue to see. We have this result holds for C star algebra, so it holds there, and some of them don't. So it's really kind of, so far we've been, it has been attacked in the literature, looking at one problem at a time. So just for one of these examples, let's see this first example here. If you were in the C star algebra case, and so we had the universal C star algebra, so recall, if you were in the C star case here, if I look at C star of this graph there, which let's call it E, C star of E, then we have the algebra, the C star generated by this partial isometry E, but subject to this relation. So this is really a unitary, right? So the C star algebra generated, but this V is really a 1. The C star algebra generated, generated by a unitary. Well, then you know that this is going to be just the C star algebra of the spectrum of this unitary. So this is going to be isomorphic of continuous right to the C star algebra of the spectrum, just the continuous of in S1, right? The spectrum of a unitary, it's just S1, right? This goes in, well, the theory of C star algebras. Okay. Oh, right. So now that we have this, I'd like to just make the connections between these two concepts. As I said, right, they're related. One is one algebra, C star algebra is the closure of the algebra. So make this connection here via partial actions, which is a very popular theme in Florianopolis. Some people say, well, maybe some people say we are the world center for partial actions. We have a large group for the studies partial actions. So a crash course in partial actions, I would just say, so I'm assuming that everybody knows what the action of a group is. So if I want to, so I'm going to start with a group, say G is a group. Let me write, well, this is going to be erased when I change to the next slide. So G is a group. And what I have here is just, I have a set X. And I have a collection of subsets. XG is a collection of subsets. XG now indexed by the elements of the group. Subsets for all elements of the group. And I have a set of bijections that goes from X minus G to XG. So that's the partial action, a set of bijections. But just that? No, I mean, it has to resemble a group action, right? In fact, generalized group actions. So if I go from X minus G to XG, so that's my bijection. And well, if you have a group you want to compose, right? You would like, for example, HG times HT. I didn't choose letters very well, but I'd like to compose, right, as in a group action. So, well, what happened here, I'm going to look at the domain of HT. I should have called this HS, but anyways. So the domain here is something, let's say here, X minus T, right? That's where this bijection is defined and goes to HT. So, well, I would like then that HT composed with HG is equal to HTG, where this makes sense, right? So I have to look at the points here in the domain of HG that fall exactly in this intersection. so that I can compose. Where this makes sense. Makes sense. So partial action, collection of subsets, collection of bijections. I would like to compose them. Of course, maybe I cannot compose everywhere, but I can compose partially. And where I can compose, I just ask for the action condition. Okay. If you're in an algebra, say if I start, instead of starting with a set, I start with an algebra, then X would be, these subsets would be ideals. If X was a topological space, the subsets would be open sets, and so on. So it depends in which category you are, you change here the restrictions. Okay. So, well, sorry about this erasing it here, but let's move. So what I say we have a shift space. So we have a graph, we have the infinite paths, and now look at the free group on the edges. And I'm going to define a partial action. So for each element of the free group, I have to define a subset. But I'm not going to, for most of them, it's going to be the empty set. I'm just going to be looking for elements of the free group that are really finite sequences. And that they have, so this AB minus 1. So I'm going to look at finite sequences that, so let's say this is A here, and then I will have another one here, B. They have the same range, this AB minus 1. So for these ones, for these elements of the free group, I look at all the sequences that start with A. So here it could be a sequence that starts here. And of course, it will be erased. Okay. So I don't know, this goes on in my graph here. So I'll have a map from XAB minus 1 into X, the inverse would be BA minus 1. So what I do, I get a sequence here that starts with A, for example, XC. And what I have to do now is to take to a sequence, to a path, infinite path that starts with B. So, well, I just erase A, right? I just erase A here, and I place B in front. So this A here, this path AXC will be replaced with BXC. Okay. So that's the action, the partial action. Okay, so these are partial action. Okay, so we have these maps. So once you have an action, we can look at this as a topological space. Okay, if you had this X here of the discrete topology, the set of all paths, these are Klopen sets. These are, we have a topology. So once you have the topology, we can look at now at the induced action at the level of the continuous functions. So if you want the sister algebra, you look at the continuous functions. If you want the Leavitt path algebra, you look at locally constant functions. Okay, but how does this induce an action? So if I look at a continuous function here, right? So I'm now saying that I had the bijections between this X, the subset X. I'm going to look now at continuous functions at each one of these subsets. So let's say I take a continuous function here. Right, the continuous function f is in here, and I have to land in a continuous function, right, of the subset of sequence that starts with B. So what I do, right, I get an element that starts with B, so I apply H. That means I take the B out, I put the A in front, and now I can apply my function f. So that's the action. And once you have this partial action here in the algebraic level, you can look at the skew ring or the partial cross product. So what is this? So this skew ring here is just direct sum, right? I had like for each XAB minus 1, I had a continuous functions of A XAB minus 1. And now I can just look at direct sum of these elements, which usually we denote this direct sum as this finite sum here, ft delta t, where delta t is just a marker telling you that you are, this ft, this function ft is in the t fiber. That's a direct sum of all these continuous functions. And so this is an algebra with pointwise sum and multiplication. Multiplication, the action takes a role. So if you multiply the function that was a fiber t with the function that is a fiber s, you just do not multiply them. You have to, the action of t here has to move around. And then there's a little technical thing that maybe I cannot apply this action right there. So the actual formula is this, but really what you're doing is just this here. If you had a group action, the multiplication would be given here. The partial cross product is the completion of this algebra with respect to a suitable norm. And then one can show that the Leavitt path algebra is isomorphic to this skill ring. This is a result of myself and Danilo Ryer. And the graph system algebra is isomorphic to the partial cross product. This is Nadia Larson and Toke Carson. They proved that. But now once we have this, well, of course, you can also go to the groupoid way. You can see these algebras as groupoids. But once you have this, you have all the tools from this partial action theory, and you can, derive some results. For example, we can prove that the Leavitt path algebra associated to a graph is simple if you don't leave the actions topologically free and minimal. Okay, so minimal means that this action that I just described to you guys has no closed invariant subsets, and topologically free is just it's kind of free. It's just that the set of fixed points by the action has empty interior. But this is just a dynamical condition, right? Minimality, topologically free, and it's being seen as an algebraic property, simplicity. And then you can also show that this happens if and only if the graph satisfies condition L and there is no hereditary saturated subsets. Well, condition L means what? If I have a loop, it must have an exit, right? So if I have a side, well, it could be something bigger, something like this, well, it has to have an exit. So this is a purely combinatory condition. And hereditary saturated sets, well, saturated is a little bit more, it's also combinatoric. So hereditary says, for example, if a vertex is in this set, then the range, and there is an edge coming out, then the range is also in that set. Okay, so this is, I find this a very nice result because you're really connecting. You just look at the graph and just from the combinatorial structure of it, you derive properties from the algebra and dynamical properties. So it connects everything. And of course, you can you have other results. For example, if you want to look at orbit equivalence, this is a very hard problem. Or conjugacy, right? So if I have two graphs, and you look at the orbits of it, I don't know. For example, two graphs like this, it's hard to tell if they are orbit equivalent. So there's a notion, right? We look at this space, the shift space that I defined to you guys, the infinite sequences with the product topology. And you want to say if these orbits of this by the shift are taken to orbits in the other one, right? So if I have U1 here and I have E2, so this has been shown that the existence of this orbit equivalence is the same as the existence of an isomorphism between the sister or the partial cross products, for example, or the groupoid between the sister algebras of the graph that takes the diagonal to the diagonal. Okay, so Toke Carson is really the expert on this in the world, I'd say, in the graphs, right? So this being, of course, this being building on this whole program that began with Ian Putnam and Herman, I think, and then Skal and all these guys, and this being, been building up, and now on graphs and things, a lot of people have contributed. So I should not mention anyone because I'll leave a lot of people behind. But this is again an in-stream problem. They have a problem in dynamics that's been rephrased in terms of analytical and algebraic problem. Okay, so this is a little bit lost here. Maybe I'll just this was just a beginning. So in the last 10 minutes, 15, I'll talk a little bit about some recent research that I've been doing. So there's some picture here of a graph. Maybe I should start with this. I'm just recalling you here, right? I have a beamer here somewhere. I think this. Let's see. Yeah. So our space is all the infinite paths. So for example, right? So if 7 can be followed by 6, I can follow by 3, followed by 2, and so on. So the question is how to define an analog for infinite alphabets. Let's say we have an infinite graph. How can I define an analog of all of this that I showed you guys to an infinite graph? So this has been studied a lot in that related to dynamical systems, right? But usually people just take the product topology, and then you get a bare space, and it's fine, it's a bare space, but it's not compact, not even doesn't need to be even locally compact. And the relations, the sister algebras that we had, we don't have them clearly, at least. So I'll just mention one thing, that this shift space can also be obtained as the spectrum of a sort of the Kunstkrieger algebra, for example, when you have a matrix, right? So this space that we're studying is related also, started with the algebra of Kunst and Krieger. I should say this is just being building from there too. So there's been many approaches to shift space over infinite alphabets. And well, of course, there's no correct one. Maybe there's one that's more adequate for one thing or the other. So I would say that for sister algebras, Toki has a recent paper that's very nice about algebras of shift spaces, but it's more in the defined alphabet. But so just taking the product topology doesn't seem to be recovering the connections to sister algebras. So Otto, Tomfer, and Willis, they have a approach that's connected to graph sister algebras. It's a very nice paper when they introduce these shift spaces, and in their definition it's compact. And Axel and Laka also have proposed a shift associated to infinite matrix, right? You just get the Markov shift, and that should be, building from the Kunstkrieger idea that the usual shift space is the spectrum of a commutative algebra. They also say, well, look, they define, right, infinite theory. So, but then, okay, we want something that maybe, when possible, put these two definitions in just one umbrella. So when you're just working with graphs and you're working with infinite matrices, and when we start to work with this, we get to the definition of ultragraphs. It's a definition by Mark Tomford that kind of encompasses both infinite matrices and graphs. Okay, so if you have an infinite graph, so I'm just, well, impossible to draw an infinite graph. I put infinity here just to say that from this vertex C, there's infinite number of edges saying, infinite number of edges getting out of C. So what is going to be my shift space? So again, I'm going to look at all here. But now we'll say I'm traveling through this road here. You can look at roads, right? Go to 2, and I get to vertex C. Well, there's infinite number of edges coming out, and there's infinite number of infinite times. So you get stuck there. So what happens? You're traveling from 1 to 2, and you can't decide. There are too many options. So we're going to have a finite sequence, and we're going to have the 2 as well. So we're going to have all finite sequences that end in a vertex where there's an infinite number of all the usual ones in the infinite emitter, right? The infinite emitter, the vertex, there's an infinite number of edges. In the set, what would be the topology? Topology is the usual one. In what for infinite sequences. So we're going to look at cylinder sets, for example, Z of 1, 2, or not Z of 1, 2. Let's take Z of 5, 1, 4, for example. So this is this is a base for the product topology, the usual product topology. So I'm going to be looking at all infinite paths that start with 1, 4. So the 1, 4, 5, 5, 5, 5, 7. So all the infinite ones. So this is a basis for the infinite sequences, okay? But for the finite sequences, for example, the sequence 2 there, I have to, well, out of the C here, I have to choose a few edges that I don't like. Okay, so I have cylinder set at 1, 2, and I'm going to choose a few edges coming out of C, say E1, E2, and I say, well, I don't like these 2. I know that I don't want to go through them. So this is going to be all paths that start with 1, 2, start with 1, follow 2, and then here, well, I don't want to go through E1, E2, so it goes to some other paths here. So we will avoid, right? You start with 1, 2, start with 1, 2, and avoid E1, E2. Okay, So this gives a topology here, which is the boundary path space of the graph sister algebra. Okay, and it's also a contour set. So that's the topology for graphs, and we're going to try to do something similar to ultragraphs. And of course, I have 5 minutes, so I'll just give you the idea of why ultragraphs are nice. Ultragraph is a labeled space. But I can also, for those who know labels, it's kind of graphs where I can give labels to the edges. But I can only label edges that are departing from the same source, same vertex. So for example, here I have 2 label ones. So in my path, I can follow 5, 1, 2 is allowed, and 5, 1, 6 is allowed, right? 5, 1, 2, and 5, 1, 6. But usually, instead of talking about label spaces, you say that the range of the edge 1 is the vertex, is a set, is BC. So that's an ultragraph. So here, just a definition. So the range, now we call this, this range that's 2 vertices or more, we call it generalized vertex. And then we have, this is just another example. We have an ultragraph sister algebra. And the definition is very similar to the graph sister algebra. You can see CK here for projection of the vertex is the sum of final projections leaving this vertex. But we also have projection for each generalized vertex. And we have to ask that these projections behave well under intersections and unions. Okay, but this generalized vertex, they are the ranges, the vertices, and you also have to allow to make finite unions and finite intersections of them. And one nice example that comes from physics and that has been studied recently by Rui, Frozino, Bissaco, and others is the one associated with the renew shift. Because once you have an infinite matrix, you can make an ultragraph where, look, for each, you just put a countable number of vertices and you read. So for each vertex, there is an edge that departs from this vertex. For example, for vertex 1 here, there's one edge, U1. And the range, you just look at where the ones are. So the first row here, there's just all ones. So the range of this edge is this whole set of vertices. Then you go to the second vertex. And the range here, look, there's a 1 in the first entry. So the range of this edge that comes out is 1. And so you get, like, if you look at the ultragraph sister algebra, you also get the same as the Exolaca sister algebra. So this is nice to study them. And I will skip all this. This was just nomenclature because I don't think I have time. So when I look at the space of ultragraphs now, right? So what's the X associated, right? Our shift space is again all infinite paths and finite sequences, as was in the graph case. But now look, for example, 1 here, I'm going to look at the edge, for example, the path 5, 1, and well, I have the range of 1 is BC, right? So instead of looking at BC, I'm going to look at just at the pair 5, 1, C, because C is a minimal infinite meter. What is that, a minimal infinite meter? So it's a generalized vertex. So there's an infinite number of edges coming from coming out from this set of vertices. But there's no other, there's no other subset where this happens. No other subset, no other generalized vertex where this happens. So for example, from BC, there's edge 2, edge 4, and an infinite number of edges coming out. So, but it's not a minimal infinite meter, because I can look at C here and look, see there's also an infinite number of edges coming out. So I'm going to look just at pairs of finite sequences with minimal infinite meters. And then I'll give a topology just like in the graph case, where I choose some edges to avoid. And my shift space is going to be just the infinite sequences union with these finite sequences. Okay. And then we have a basis for the topology. That's what I mentioned. And then you can show that this space is nice. Has a basis, has a countable basis of Kloppen sets. Is metrizable. So we can do really dynamics here with this metric. And well, it's not true in general that this basis of compact sets. Well, it can be done, but we will need, like, there's some examples where this does not happen. So we usually restrict ourselves to graph that are fun. Because when we have this basis, it's nice. So this is not a too restrictive condition. It just asks that the range of each edge is a finite union of minimal emitters or just of single verses. All this can be, you ask, can be done in general, yes. So I've done with Gilles and Danny Van Wyk, Gilles de Castro. We have done the general construction, but then you cannot get a space as just infinite sequences. You have to deal with filters, ultra filters, and we have showed that this is kind of optimal in the way of getting a space that resembles, that's really, you know, infinite path space of sequences of edges. Okay, so with this space, then well, we have a shift map as we just erased, and here I'm defining as if we have an infinite sequence of element of length 0, then you just repeat itself. But usually we just take it out and look at this as a local homeomorphism. Okay, so I'm just saying here, I'm just going to give you an example, another example of the renew shift, where now the space is just all infinite paths and the paths that end at A, right? So the edge ends at E1 at the first edge. Okay, that will be the space. So just we say that with Danilo Royer, we have proved some result about conjugacy. So if the shift space are conjugate, then the sister algebras are isomorphic. With actually, this isomorphism takes diagonal to diagonal, intertwine the gauge actions. And a similar result holds for Leavitt path algebras. I didn't say, but there are Leavitt path algebras of ultragraphs, so they're also interesting to study. Although, right, Leavitt path algebras of ultragraphs and the sister algebra, they're always Morita equivalent to the sister algebra of a graph or infinite matrix, but not isomorphic. So they're examples of algebra that are not isomorphic. So it's interesting to see what holds there, of course, apart from Morita equivalence, right? And so further topics, right? Much what I showed can be done via groupoids. So you can look at the path groupoid of a graph, and here there's how the whole theory of groupoids that I would say is more developed than the theory of partial action and so on. So you can even apply more results. You can look at continuous orbit equivalence, full groups, their invariants. If you want to look at ultragraphs or their generalizations, you can look at Leavitt path algebra results. Since we have a metric space, you can really look dynamical systems. So I have done with Bruno Gioni a study like Lior chaos. For this, what's nice, this is a purely dynamical paper, is that we could show that this space that we have properties that are usually satisfied for finite alphabet shift spaces. But if you just look, at the product topology as people usually do, then these results do not hold. But for these shift spaces that come from sister algebra, from algebra, then they do hold. So this is nice. So you can try to get your favorite, result in symbolic dynamics and try to generalize it to ultragraphs or other kind of shift space that come from sister algebras. I find this is interesting. So we can look at, symbolic dynamics is a whole world here of possibilities of further studies. Okay. So I'll stop here because I think I already went over time. So thank you for your time.
Obrigado.
Thank you very much, Daniel, for a nice talk. Does anybody have any questions or comments for our speaker?
I just want to say thanks a lot for coming. I really enjoyed the talk.
Thank you. I didn't see who said that.
Tim said that. Tim.
Oh, Tim. Okay. Thank you.
I was going to ask, you may have said this and I missed it, but do you have cases where you have conjugacy and of the system, but the sister algebra is failing to be isomorphic? I mean, because that can happen in a cross product C-star algebra. I was wondering if in this setting, do you have any of those kind of pathological examples?
I don't think so. If they're conjugate, if the systems are conjugate, then usually you get a if the systems are conjugate, you get a homomorphism between the groupoids, because you get a homomorphism between the unit space of the groupoids, and the groupoids are going to be isomorphic. Yeah.
Okay.
At least in this at least if our definition of conjugacy, right? But yes.
Yeah, because I mean, there's examples of actions on like automorphisms on a topological space, which isn't conjugate to its inverse. But the C-star algebra, because it'd be just a single action, so it's a amenable.
Right.
The C-star algebras are turned out to be isomorphic because the system doesn't notice the difference between a forward and a backward, but they end up not being conjugate.
Right,
and-
the flip conjugates.
Yeah.
But is that for conjugate? Is that not for orbit equivalence?
I thought it was for conjugacy.
For
This was the
conjugacy.
kind of how the introduction of the semi-cross product was kind of based on trying to solve this, like the non-self-adjoint rather than the C-star algebra, operator algebra.
But our space is connected. Maybe you need a connected space for that.
Maybe.
Yeah. But I think here it doesn't happen. But okay, yeah, maybe this can happen.
Yeah, I was just curious because it's a very weird example, which I think like the work of Putnam and stuff you mentioned was they look at certain spaces where this doesn't happen.
Okay. Yeah, I think here is okay.
Okay.
You're safe.
Any other comments or questions for our speaker? Well, I thank you once again. I even put a little clapping hand there for you.
Okay.
And if you don't mind, those of you who are in attendance, we could turn your cameras on and we can have a group picture. Don't be shy. Very nice. Okay, I'm gonna count till 3. So you have plenty of time to smile. 1, 2, and 3. Another one for good luck. Thank you so much, Daniel. It was nice seeing you. Very nice talk. And
Thank you.
And we appreciate it.
Thank you too. Have a good week.
Happy holidays, everyone.
Yes, let's see if that.